In the last lecture and the previous one, we talked about Shor's error correction codes, talking about 3-qubit error correction code. As we have seen, this is not a complete code and takes care of bit flips, but let's talk about a more general code which will take care of both bit flips and phase flips. But before doing that, let's make a few observations which are the reasons which we are going for error correction. We said that the quantum states are extremely fragile. They are likely to easily decohere, and that happens by interactions with surroundings, and it is necessary that we maintain a coherent superposition of multi-qubit quantum states if we want to do any quantum algorithm satisfactorily. And this becomes a difficult task because of the fragile nature of the qubits, and the qubits do not maintain their coherence. So bit flips are not the only errors that are possible in a quantum state. Continuous evolution of the quantum states also induce, as we said, phase errors, and while a general overall phase error is unimportant for a quantum computation, for the simple reason that two states which differ by an overall constant represent the same state, if there is a relative phase between the components of the same states, then of course that creates a problem. So for instance, suppose I start with an initial state which is 0 plus 1 divided by square root of 2, and let us suppose that a phase perturbation occurs to a state which has a relative phase between them. For example, 0 plus e to the power I alpha 1 divided by square root of 2. Now if you make a measurement of sigma z, you will still get either 0 or 1. Well, in this particular case you have 0 plus 1 by square root of 2, so therefore the sigma z expectation value will be half for both 0 and 1. But however, if you made a measurement of sigma x, remember the original state was an eigenstate of sigma x with an eigenvalue plus 1. But now what happens is this: because of this relative phase, we have seen earlier that the eigenvalue plus 1 and the minus 1 will not be 1 and 0 respectively, as would have been the case if there was no relative phase error, and it would depend upon how much the phase is affected. So let us look at what can one do for the phase error. One of the things that we would like to do is to talk about a phase error due to rotation of a qubit by an arbitrary angle phi. But in order to make discussion somewhat simple, let us just take the case of phi equal to pi. Now if phi is equal to pi, then a0 plus b1 goes to a state a0 minus b1. Now you notice one thing, that supposing I look at the case, special case of a equal to b equal to 1 over square root of 2, then this simply means a state 0 plus 1 by square root of 2 has become a state 0 minus 1 by square root of 2. Now but it may be observed that while 0 plus 1 by square root of 2 going to 0 minus 1 by square root of 2, but suppose you are looking at it in a diagonal basis. Now if you are looking at it at a diagonal basis, 0 plus 1 by square root of 2 is nothing but the state plus, but 0 minus 1 by square root of 2 is the state minus. So it means what was a phase flip of pi in the computational basis is actually a bit flip in the diagonal basis, and this is a useful information to have, as is shown in the diagram that I'm showing you here. So look at this. This diagram shows this is your computational basis 0 and 1, and the diagonal basis, they make an angle of 45 degrees with the computational basis. So this basis is plus and minus. Now suppose I consider now an arbitrary state psi. Now let's look at what it actually means. Now if you are looking at a computational basis, then this psi, which has this component, the 0 component is this much, this is shown by this dotted line here, and of course the component 1 would be from here to there. Now so if there is a, let's say, bit flip, Now if there is a bit flip, what happens? 0 goes to 1 and 1 goes to 0. Now that would make this state go to this point, because all that it means is the width here would be the same as the width here, and the length here would be the same as the length there. So this would be a bit flip. Now if you look at this geometrically, it simply means that this is a reflection of the state psi about this diagonal basis. On the other hand, consider a phase flip. Now what does a phase flip do? So you have A0 plus B1, and let's suppose it has become A0 minus B1. Now you can immediately see what will this become, and since we have seen that a overall phase doesn't matter, then I can bring this back and say that this state is here. If this state is here, then it simply means this is a reflection about the, if you want to call it the vertical direction, the vertical direction. So there is a nice geometrical interpretation which shows that the bit flip in one phase may become the phase flip in another basis. So let us look at what we could do to take care of the phase flip error. And so what we need to do is to talk about encoding the triplets in a diagonal basis. Now if you do this, that this is your diagonal basis, and you want to compute this in a computational basis. Now this is fairly simple. As you know that plus stands for 0 plus 1 by square root of 2, minus stands for 0 minus 1 by square root of 2, and what you do is you simply multiply them. Now if you multiply them, you will find that this will naturally give you 8 states there, because this is plus 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 and this is minus minus minus, and this is what you would then get 0 0 0 0 1 1 1 0 1 1 1 0, and with a minus b by 2 square root of 2, this thing. Now let's see what would happen if you did a measurement of any one of the qubits, and we have illustrated it in the computational basis. So suppose I make this measurement in the computational basis. Now let's measure basis number 1. Now if you look at the basis number 1, flipping between the two slides, you notice here the qubit 1 which I measure will either have a value 0, in which case that the system would collapse to this term, this and that. Alternatively, the qubit 1 could collapse to value 1, in which case I will have a plus b by 2 square root of 2, this state plus this set, and a minus b by 2 square root of 2, this state plus that state. This is what is illustrated here, that the state collapses either to the state on the first line for which the first qubit has a value 0, or to the state which is on the second line for which the value of the first qubit is 1. Now let us suppose that it has collapsed to the first state. So first state, as I had shown you here, is a plus b by square root of 2 0 0 0 plus 0 1 1 plus a minus b by square root of 2 0 0 1 plus 0 1 0. So now what we do is this, that we need to do a parity check in the diagonal basis. Now how is it done? This is done by introducing two ancilla and measuring the ancilla after the C0 operation, as we had done and discussed it in detail while discussing 3-qubit code. So in the diagonal basis, my collapse state is a times plus 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 b times minus minus minus, or a times minus plus 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 b times plus minus minus. You notice what has happened here. What happens is this, that this is of course without error, because that is what we started with, and this says that there is a single bit flip error, but this bit flip error is in the diagonal basis, and this we can take care by doing the corrective action as we talked about in the 3-qubit basis. So we will now go to a situation where we take care of bit flip as well as phase flip in the same code, and this is known as Shor's 9-qubit error code. Now this error code takes care of bit flip error. We know that bit flip error arises because of application of an X gate on the state AB, and that gives me BA. On the other hand, a phase flip error is taken care of by a operation of a Z gate on AB, which gives me A minus B, and if you have both phase and bit flip errors, that's essentially equivalent to a Y gate, and this is, of course, there is a overall factor of I which one has to take care, but the Y gate acting on AB gives you minus BA. So these are the three types of error that we would like to take care, and that is what Shor's 9-qubit code takes care. Now let us see how does Shor's 9-qubit work. So in Shor's 9-qubit, what we do is we encode 0, as we had said several times, as 0 logical, and this is encoded as plus plus plus, and 1 is encoded as 1 logical, which is minus minus minus. So what actually happens is the following, that we are interested in sending through a quantum channel a state A plus B1. So the thing is this, I am showing the circuit here on the slide, and I will go on explaining what does this encoding circuit actually do. So first thing is the following, that we want to do what I have called as the phase flip encoding. Now, so I start with A0 plus B1, and the first thing that we will do is they introduce two ancillas here. Going back to the slide, you can see it here. Under the green thing, I have introduced two ancillas 0, 0, and I had started with psi, which is A0 plus B1. So what do I have is this, I have A0, 0, 0, writing it in all the 3 qubits together. I have B. Now let's look at what has been done here on the slide. So the first ancilla bit and the second ancilla bit that we have introduced, I use a C0 gate with the psi as the control. And since psi is A0 plus B1, so A0, 0, 0, nothing happens on the C0, but on the other hand, B1, 0, 0 becomes B1, 1, 1. So that is the effect of inside this slide if you look at this step here. Now having done that, what we do is to apply Hadamard gate on all these 3 qubits. Okay, let us look at what we get. So we would have A. Now there are 3 of them which are being used for Hadamard gate. So I will get A by 2 square root of 2. Then I have 0 plus 1, 0 plus 1, 0 plus 1, and likewise the second term, which is B by 2 square root of 2, 0 minus 1, 0 minus 1, and 0 minus 1. So this is the result of this Hadamard gate which is shown in the slide. Now at that stage what we do is this, that after the Hadamard operation has been done, we introduce 2 more ancilla with each of the 3 qubits there. Remember, I started with 1 qubit, introduced 2 ancilla, subjected this ancilla to first a C0 gate and then a Hadamard on all 3 gates. Now what I do is, each of these 3 I introduce 2 more ancilla. So that is the reason for calling it Shor's 9-qubit code. So let's see what we do in with this. So what we are going to do is the following, that remember now, go back to the slide again, we'll switch between slide and this. So this one was that 0 plus 1 by square root of 2 in one part and 0 minus 1 by square root of 2. These were the three states which were entangled together. Now I have introduced two more ancilla which have been put at 0, 0. And what I do is, to each I apply a C0 gate as the way it has been shown. So line 1 acts as the control, does the C0 gate on line 2 and 3. The qubit 4 acts as the control, does on 5 and 6. Qubit 7 acts as the control and applies the C0 gate on 8 and 9. So what happens when we do that? So we had, of course, remember I had a by square root 2 square root of 2. So to start with, I have this. These are the 9 states that I have. 0 plus 1, and these are the two new ancillas that we have put in, 0, 0. Again multiplied by 0 plus 1, 0, 0, 0 plus 1, 0, 0. And likewise I have b by 2 square root of 2, 0 minus 1, 0, 0, 0 minus 1, 0, 0, and again 0 minus 1, 0, 0. Now what happens is this, that we are applying, using this as the control, C0 on each of the bits. So look at what will I get. I will get a by 2 square root of 2. I will now need to write them down together. So in the first block of 3, I will get 0, 0, 0 plus 1, 1, 1. This is the effect of C0, and since these are identical situations, I will get 0, 0, 0 plus 1, 1, 1 and 0, 0, 0 plus 1, 1, 1. And then plus b by 2 square root of 2. I get a very similar structure, excepting that the plus sign between the each block qubits becomes minus 1. Now, instead of writing these 9 things together, what I will do is call this thing here as plus plus plus. So this whole combination, we will say a by or a times, I will say this is plus plus plus. So this is the shorthand notation for this thing, that each plus stands for 0, 0, 0 plus 1, 1, 1, not to be confused with 0 plus 1 by square root of 2, that as we have been doing, and plus b times minus minus minus. So what I have done basically is to start with 1 qubit, introduce 2 ancilla, and then do certain operations on those 2 ancilla, so that I have 3 qubits at the end of the first group, and then with each of these modified groups I apply 2 more ancilla, and then I have 9 qubits, and this is the final coding that I have received. Now what we do is this, let us assume that out of these 9 qubits that are going through a noisy channel, at most 1 qubit may be affected. Let me say that P is the probability that a single qubit is affected. Now, when I say affected, it means it could be either a bit flip or a phase flip or a mixture of the two, bit flip along with the phase flip. So then the probability that no qubit is affected is clearly 1 minus p to the power 9. Let me also tell you, typically you don't expect a very noisy channel, and this p is usually a small number, and I expect it to be usually much less than even 0.01 or so. So since p is small, I can expand this 1 minus p to the power 9 in a binomial series and get this as 1 minus 9p plus 9 into 9 minus 1 by factorial 2 p square, and so that is equal to 1 minus 9p plus 36p square. The probability that a single qubit is affected is clearly the case where any of the 9, and hence a factor of 9, is subjected to an error which is p, and the remaining 8, which is 1 minus 8 is 1 minus p is the probability raised to the power 8. Now expand this also in a binomial expansion. The term is simply 9p, because this expansion is 1 minus 8p, okay. So that is, so let us write this down. So 1 minus 8p, then of course you have plus, etc., etc. So this quantity would be 9p minus 72p square. So if you now try to find out what is the probability that I have either 0 error or a maximum 1 error, is simply obtained by adding up these two. So I had here 1 minus 9p plus 36p square, and I have 9p minus 72p square. So therefore, which is simply 1 minus 36p square, which means the probability of having more than 1 error is just 36p square. And since we had said that probability p is small, so this is of course a much smaller than p with which we started. So that essentially is the coding circuit of Shor's 9-qubit code. We will start from here, and in the next lecture we will try to see how decoding of such a circuit will be done.